Okay, so we already saw in a previous video that now that we talk about observables and their real outcomes to each measurement, we could also talk about the expected value of a measurement. So of course a measurement outcome is probabilistic, and so we could talk about the statistics of what we expect to see. So in this video we are going to look at this question a little more precisely and closely. So let's say that we have an observable M. So M is a Hermitian matrix. So M equal to M dagger. It's a k by k Hermitian matrix. And let's say that we have a quantum state of our system, which we now write in the eigenbasis of M. So we write it as summation alpha I phi I. And so now if we measure this observable, we get a random outcome. And let's let the random variable x denote the outcome of this measurement. Okay, so what we want to do is we want to understand what's the distribution of x. So, well, of course, this is sort of easy to do because we know that what are the outcomes going to be? Well, they are supported on the eigenvalues of M. So if the eigenvalues are lambda naught, lambda 1 through lambda k minus 1, then we know that lambda I will occur. So the probability that x equal to lambda sub j is just what? Well, the jth outcome will occur with probability alpha sub j magnitude squared. Right? Because our state psi, which is the state of our quantum system, we have decomposed in terms of the eigenbasis of M, and the amplitude of phi sub j is exactly alpha sub j. So we get a probability distribution of this kind on our j different outcomes, on our k different outcomes, lambda naught through lambda k minus 1. Every other outcome has probability 0. Okay, so now we can try to, well, of course, ideally we'd want to know the entire probability distribution, but usually we collect some statistics about this distribution, and that gives us a rough idea about what this distribution looks like. And so the two most useful, the first order statistics are the mean of the distribution, the expected value of x, which we might denote by mu, and the variance of x, or sigma squared, where sigma is the standard deviation. The variance of x is the expected square of the deviation from the mean. So it's the expected value of x minus the mean, the whole square. Okay, so I'm sure you all know about these quantities, but let's just try to make sure that you understand them. You have a feel for what these two quantities are. So we are given some probability distribution, and we might, you might imagine that you actually make a wooden cutout of this distribution. So you make a wooden shape which looks like this. Okay, so then what's the mean of the distribution? Well, it's the point at which you can balance this distribution, right? If you think of this as a seesaw, then this is exactly the middle point, the point across which, if you hold it at this point, then what's on the left and what's on the right exactly balances. Now, what about the standard deviation, or the square root of the variance? How do you interpret that? Well, there's also a very nice physical interpretation of that, which is that if you were to rotate this shape about this mean position, so you rotate it about this vertical axis, and then you try to feel how much moment of inertia there is. How difficult is it to rotate this shape, right? Well, then this the standard deviation is exactly sort of if you were to replace this complicated shape by this simple shape where you put half the mass, half the total weight of this shape on the left here, half on the right here at distance exactly sigma over 2 on each side. Then, oh sorry, at distance exactly sigma, plus sigma and minus sigma. Then this would be a shape which has exactly the same resistance to rotation, right? And the reason is that the moment of inertia comes from the expected square of the distance from the mean, from the center of gravity, and in this case, we are achieving the same squared distance on average from the center. Okay, so now let's try to approach this from a more quantitative point of view. So we have an observable M, state sigma, and we want to understand what the mean value of this, of the outcome of this measurement is. And I claim that it's given by bra phi m ket phi. Okay, so let's try to prove this. So let's say that M had eigenvectors phi sub j with eigenvalue lambda sub j, and let's say as before that psi we wrote as summation alpha sub j phi sub j. So we wrote our quantum state out in the eigenbases of M, and these were our amplitudes. So now what's the expected value of x? So mu, which is the expected value of x, is what? Well, we have outcome lambda sub j with what probability? Well, the outcome is lambda sub j if we happen to project onto the jth eigenvector, which happens with probability alpha sub j magnitude squared. And so the expected value is the sum over all j of this. Okay, so now what we want to show is that this is exactly the same as that quantity. So let's write out that quantity. Okay, so what's ket psi? Well, if you were writing in the, let's write out, it depends upon which basis we write it out in. So let's write out ket psi in the basis of eigenvectors of M. So what does ket psi look like? Well, it looks like exactly this. It looks like alpha naught, alpha 1, alpha k minus 1. What does M look like in the same basis? If we are writing out M in the eigenbasis, well, then it looks like lambda naught, lambda 1, lambda k minus 1, 0, 0. So it's a diagonal matrix in its own eigenbasis. And what's bra phi? Well, bra phi is the row vector corresponding to this. It's alpha naught star, alpha 1 star, complex conjugate, alpha k minus 1 star. Okay, so you multiply this out. What do you get? Well, you follow your rules of multiplication, and you get summation lambda sub j times. Okay, so sorry. Let's write it out in proper order. It's alpha sub j star lambda sub j alpha sub j. These are all complex numbers. These are complex numbers. That's real. They commute with each other. So you can just write it as summation lambda j star, alpha j star, alpha j lambda sub j. And what's this? What's alpha j star times alpha j? It's just the square of the magnitude of alpha sub j. Okay, so this is all equal. Okay. What about the variance of x? So sigma squared. Well, I'm sure you know the variance of x is you can write it as the expected value of x squared minus the expected value of x whole thing squared, which is okay. This is just expected value of x squared minus mu squared. Okay, so So what are we claiming about this? We are claiming it's this bilinear form. It's bra psi m squared ket psi minus bra psi m ket psi whole squared. Well, you can see where this second piece comes from. This is just mu squared. So what about this first piece? Well, okay, so what's the expected value of x squared? So what's x squared going to be equal to? Well, if we had the jth outcome, then the square of the outcome is just lambda j squared. And with what probability does it happen? Well, it's still the same probability. It's the probability that we project onto phi sub j, which is alpha j magnitude squared. Okay, sum over all j. So that's what the expected value of x squared is. Now, what's this bilinear form? Well, this bilinear form is, again, it's bra phi, sorry, alpha naught star, alpha 1 star, alpha k minus 1 star, times, what's m squared when written out in its eigenbasis? Well, you can square this matrix. What will it look like? Well, it'll just look like it's a diagonal matrix. It'll look like lambda naught squared, lambda 1 squared, lambda k minus 1 squared. So when you square a matrix, its eigenvectors remain unchanged and its eigenvalues get squared. And so, of course, now you can see that this is clearly equal to that.